Now there's another thing we can also do with our model. We want to see how great the model is. We can give an assessment so we can assess the model properly. So we can do that by assessing the goodness of the fit of the model. So how do you do this? To do this, we can look at a couple of different metrics too. So what are these metrics? We call one multiple R squared. So the multiple R squared is a measure of the strength of a linear relationship between between the predictor variable and the response variable. So a multiple R squared is of 1 indicates a perfect linear relationship if the multiple R squared is 1. So while a multiple R squared of 0 indicates no linear relationship whatsoever. So the multiple R is also the square root of the R squared, as you know in statistics, which is proportional. This is the proportion of the variance in the response variable that can be explained by the predictor variable. So in this example, which you gave here, the multiple R squared is 0.775. So here, so if you take a look here, so it's called the adjusted R squared is 0.75 0. This is a multiple R squared. So the multiple R squared is 0.775. So they R squared, if you try to square this, so let's use a calculator. If you do the 0.775 squared to the power of 2. Let me do that. So that gives us 0.6045. So this is approximately 0.60. So this indicates that 60% of the variance in MPG can be explained by the predictors in the model. So if you have 60% of the variance, which can be explained by the predictors in the model, that seems to be something we want to talk about. So what is a good R squared value when we say is it what makes an R squared value a good one? So this can be a discussion for another day. So if you want to know, we can do some more statistical analysis to make you know what makes it a good one. So, but we know that the value of R squared can range from 0 to 1. And the value of 0 indicates that the response variable cannot be explained by the predictor at all. So a value of 1 indicates the response variable can be perfectly explained without an error. So in practice, we will likely never want to see a value of 0 or 1 for R squared. Instead, you're going to see something, you can encounter something between 0 and between 1. So this is how we usually have it. So, but if you want to go deeper into that, you can we can have another day for it. So another thing we need to look at in our result here is called the residual standard error. So the residual standard error is this. So what does that word mean? It's the measure of the average distance that the observed value falls from the regression line. So the average distance that the observed values fall from the regression line. So this example, it's observed to be 3.008 from the regression line. So we can also say, what do we mean? Does that appear to be something good? Does that appear to be something we like or something we don't really want to talk about? So it depends on how much you want to go deep into your analysis. So, but from what we say, what makes it a good one? So this is the standard error we have, and on a degree of 28 degrees of freedom. So all of these, they have their own meaning, terminological meaning. So now let's use the model to make prediction. we've had a model now, let's make a prediction. So making prediction with the model. Making prediction with the model. So now from the output of the model, we know the fitted multiple linear regression, we know what it's equals to. So we call that the MPG hat. We call it MPG hat. Let's see here. I will need to use a keyboard, but I will not I will not waste my time. I will just write the formula straight. So the first thing we want to do is we would multiply these the MPG hat is going to be equals to negative 19.3, which is the estimated standard, which is the estimate for the intercept. So minus, so it's going to be, let's just MPG hat, supposed to be underscore, but I'll try to see if I can. Hat. So MPG hat is equals to negative 19.343. We finish 3.4. So then negative 0.019, then times the displacement. So the displacement minus 0.3122 times the HP, then plus 2.7 2.715 times the DL. So we can use this. So we can use this equation to make prediction about the MPG. So to know about the MPG would be for a new observation. So for example, we can predict the predicted value for the MPG for a car, which has got the same attribute. So we can do these also for multiple events. So once you've been able to have the values, you can make predictions with them. So, and if you want to do that, we can actually use the R. Let's define the coefficients for the model first. So then we're going to use that to make a prediction. So let's try to make a prediction here. Let's do that by defining. Let's define first. Define the coefficients. The coefficients from the model output. So let's talk about the intercept. Intercept is a coefficient summary, then model. So then intercept. Intercept. Also the estimate. So this is what the intercept is. So what about the displacement? So now I've actually written the displacement coefficient summary model. So the HP coefficient summary model, HP estimate. So this is how we should use the formula. So now let's use this model. Use the model. Use the model coefficients to make a prediction for the value of MPG. So now let's say, for example, we have let's say we have displacement equals, let's say we have a displacement equals to 20. We have HP, so we have HP equals to 150, and we have DR80, which is equals to 3. So how would you use your model to predict the MPG? So it's pretty easy. So you would just say intercept, as we did before. Intercept plus displacement times 20 to 20, then plus HP times 150, then plus DR80 times 3. So when you do this, and let's run it. So there is an error here. Oh, now we had an error the other time, so I try to fix it. So intercept coefficient summary model. So then intercept estimate, displacement estimate, HP estimate, and DRT estimate. So we're trying to see how we can define the coefficient from the model output. So now we had an occurrence here, but we had a question. We want to use the model to make a prediction when we already know the displacement is equals to 220, and we also know the HP to be 150. So, and we know the DR, then we know the DR80 to be 3. So if we know this, can we predict the MPG? And let's see if we can do that. So once you see everything looks set, you click on run. So we had a prediction. We had a prediction of 18.573. So this is telling us that the MPG would be 18.757 if the displacement is 220, HP is 150, and the DRT is 3. So this is the way we can continue to make predictions once we have the values. So the MPG is this. So we have something 21 here. So we have we can try to use some of these figures. Let's try to use some of these figures, and without using the MPG, let's use the for the Hornet sport about. So Hornet sport about is got 18.7 MPG. So we know the displacement is 360. We know the HP is 175, and we know that the RAT is 3.15. Let's use a model to make a prediction and see if we're going to get something that looks sensible. So let's replace these. Let me just copy this. So let's do it and see if it's going to work. So let's open a new cell. So for this no cell, we paste this, but we would remove the displacement is 360, and the HP is 175. 175, and the DRT is 3.15. So let's run it. And mind you, we already know that the MPG is 18.75, but we want to be sure if the model is working fine. So the model predicted 15.50. So let's double check. The DRT is 3.15, the displacement is 3.3. So the model is working, but sometimes it's not going to be 100%. So it says, so let's try another one. So this is how you can manually try the accuracy of your model. Let's do for the Mazda, where we have the displacement. The MPG is 21.0, and the displacement is 160, and the HP is 110, and the DRAT is 3.90. All right, so let's go and use this to let's change the values. So the displacement is 160, and HP is 110, and the DRT is 3.9. I think 3.90. So let's run this and see. So it predicted 23.4, whereas the real answer is 21.0. So it's 2.4 far away from the value. So sometimes we could have little differences in the values from the normal value from what we have. So this tells you your model would not be 100%. So when we saw the model, the other time it said it's 60%. So, but at least this is a model that gets something close to what the answer is supposed to be. So this is how we'll continue to make a model, and we can also test more. So, but mind you, the number of data we train also it's a factor in what affects our data. So if the data set is not too much, so you're not expecting to get a good model. So this is another thing we need to look into. So, and if I view the data now, the data frame is 32/4, so it's not enough. So we need to get more data to be able to make a better model. So all of these is things we can continue to do by ourselves until we get used to them. Thank you very much, everyone. I wish you the best.